Hello everyone, myself Dr. Prasad Puthiyillam. I'm back with the chemistry topic. Earlier it was engineering chemistry. All the videos of previous scheme, that is 21 CHE122, is available in my YouTube channel, My Intuition MI. This is the video for chemistry for a computer science and engineering stream. This year onwards, 2022 onwards, the university has changed the scheme for computer science and chemistry syllabus, for electronics and communication stream separate, and for mechanical or civil separate. So four chemistry syllabuses are available for first year VTU engineering students. So this particular class video covering the important points on a given topic, the questions and which indicating the revised Bloom's taxonomy level, as well as their answers, how to answer. Mainly I'm focusing on level 3 and level 4 questions. So this is module 1 part 1. So this is the syllabus for module 1. Sensors and energy system. Sensors, in which introduction, working principle and applications of conductometric sensors, electrochemical sensors, thermometric sensors, optical sensors, sensor for the measurement of dissolved oxygen, electrochemical sensor for the pharmaceutical surfactants, hydrocarbons, electrochemical gas sensor for sulfur, oxides of sulfur and oxides of nitrogen, disposable sensors in the detection of biomolecules and pesticides. The second part of module 1, that is energy system, introduction to batteries, construction, working and application of lithium ion and sodium ion batteries, quantum dot sensitized solar cells, its principal properties and application. Then there are self-study topic like type of electrochemical sensors, gas sensors in which oxygen sensor and glucose sensors are covered. So this this particular class video covers the sensors introduction part, the working principle and application of conductometric sensors with the important questions based on different Bloom's taxonomy level 3 and level 4. I'm focusing mainly. Level 2 questions I am not taking because it is either defining or memorize. So a little bit application oriented questions covering in this particular class video. So in introduction to sensors, here I wrote as a one point just to make sure that it is a point. Okay, I'm giving only the important points related to the given topic. To count how many points are there, I'm given that number is there. That number does not indicate any other meaning. There's no other meaning. So a sensor, it is a device which can detect and measure the presence of specific chemical or physical parameter in a given environment. So we usually say, does he have any sense? A sense means it has the ability to measure something or to calculate something or to do something. Okay, so in case of chemistry point of view, a sensor, it is a device, man-made device, which can detect and measure the presence of a particular chemical, or even it can sense a physical parameter like temperature, pressure. All those it can measure, as well as it can give the qualitative, quantitative also it can give. The second point says that the sensor usually contains a sensing element that interacts with the target analyte, generating a signal that can be detected and quantified. So it has got a chemical substance which is used to sense the target analyte. Analyte means the one which you want to analyze. So there is a target analyte. We want to target some. You want to measure some particular gas. Say we want to measure the carbon dioxide. So carbon dioxide becomes the analyte. The chemical which is used in the sensor, that we call as the sensing element. Okay, so the target analyte generating a signal that can be detected and quantified. Quantified means converted into how much quantity amount is present based on the sense which it did. Third point says that sensors are devices that detect and respond to changes in the environment or the state of a system. Okay, the same thing. What are the changes in the environment? If any gas molecule concentration changes, it shows the change in the environment. If the temperature changes, it is a change in the environment. So that can be detected by using these sensors. In chemistry, sensors are often used to detect the presence or concentration of specific molecules in a sample, such as gases, ions, or biomolecules. So, chemistry people in their research and development wing or in chemistry related industries, they use sensors mainly for calculation or identification of a chemical compound. Either it may be in gaseous state or it may be in liquid state. Liquid state means it becomes ions, or even biomolecules like bacteria, viruses, micromolecules, other proteins they can be detected by using the sensors. Chemical sensors typically consist of a sensing element and a transducer. The sensing element, that is the one which is used to sense. Say if you want to sense carbon dioxide, we use some other chemical in the sensor, which we call as the sensing element. As well as it need a transducer. Transducer is a new word, that's why I underlined in bracket I gave. It is a device which convert one type of energy into another type of energy. For example, a microphone, it is a transducer that converts sound energy to electric energy, and a speaker is a transducer that converts electric energy to sound energy. So here I am using a microphone. A microphone, it converts my sound energy to other form of energy, and through the speaker it gives back the sound what I'm pronouncing now. Okay, so these are we call as the transducers. They are the devices. So a sensor mainly consists of the sensing element and a transducer to convert that whatever sensed to another form of energy which can be used to analyze. These elements is a material that interact with the light to produce a measurable signal, while the transducer converts the signal into useful form, such as an electrical signal or a visual display. There are many types of chemical sensors, which include optical sensors, electrochemical sensors, mass-based sensors. Okay, they contain the sensing element. Some of the chemical compounds are used as a sensing element. Then it comes under the chemical sensors, which include optical sensors. Optical means something related to light. Electrochemical something related to chemical movement and in which electron movement is present, and mass based sensor measuring the mass of a substance or a related mass. Each type of sensor has unique properties and advantages, and the choice of sensor, it depends upon the specific application. So we have can have different type of sensor based on the application that we have. Not the same sensor used for all the application. Different sensors are used for different applications. Chemical sensors can be selective or non-selective. Selective sensor which respond to a specific analyte or class of analyte, while non-selective sensors they respond to a range of analyte. Okay, so if it is selective sensor, then it will sense a only particular element or particular molecule which we want to sense. The other presence or their absence, it will not be sensing. Whereas non-selective sensor, it gives a large amount of molecules. If the present different molecules present, that will be sensed and it will give the results. 10th point, the selectivity can be achieved through the use of a specific sensing element or through signal processing and algorithms. So you use a specific sensing element, that is a chemical that we use in the device, and with the support of a signal processing algorithm. So it is a it's a mathematical operation. Signal sensing or signal processing algorithm is a set of mathematical operations that are used to analyze and manipulate signals, which are a representation of data over time or space. Chemical sensors have many applications in chemistry, biology, environmental science, and other fields. They can be used to monitor environmental pollutants, detect the diseases, that is biomolecules, measure food quality, control industrial processes. These are the some of the applications, important applications of a sensor. As the field of sensor develops and continues, lot many researches are going on in field of sensor by chemists or R&D people. New sensors are increased with increased sensitivity, increased selectivity, portability are being developed for a wide range of application. The sensitivity means how it sense. Or what is the ability to sense, we call it as sensitivity. Selectivity means how exactly it is choose a particular element, that is a selective selectivity means. Portability means a device, if it is a very big device, it is very difficult for us to carry to the field where we want to use it. Portability means if it should be very handy. then such a sensors can have better market value that can be used easily in the actual field of work. First question. Explain the different types of sensors and provide an example of each type. So this is revised Bloom's taxonomy level 3 question, that is level 3 question. Uh, you need to explain different type of sensors with example each. So sensors can be classified, the answer is given here. Sensors can be classified into several types based on their physical and chemical properties. Point 1. Answer. Point 2. One type of sensor is the temperature sensor, which measures the changes in temperature by detecting changes in resistance or voltage. For example, a temperature sensor is a thermistor. It is a type of resistor that changes its resistance respond to changes in temperature. As temperature changes, the resistance of that material used that will change. So if the resistance changes, it indicates the temperature change. So it can be measured qualitatively as well as quantitatively. Third point, another type of sensor, it is the pressure sensor, which measures changes in pressure by detecting changes in force or displacement. For example, pressure sensor is a piezoelectric sensor. It generates a voltage in response to changes in pressure or vibration. If there is a change in pressure or there are any vibrations, are there any movement, is the displacement. Displacement means that is related to the pressure. If any displacement is there, that means a pressure changes there. So a piezoelectric sensor can be used as a pressure sensor. Fourth point, that's third type of sensor. They are optical sensors which measure the changes in light intensity or the wavelength by detecting changes in absorption or reflection or scattering. Example of optical sensor is a photodiode, which converts light into a current, which can be measured and used to detect changes in light intensity or wavelength. A fourth type of sensor is the chemical sensor, which measures changes in chemical composition by detecting changes in electrical or optical properties. An example, chemical sensor is the pH sensor, which measures the changes in the concentration of hydrogen ion in a solution by detecting changes in the voltage or current generated by the solution. Next question, if I take it is analyze the role of sensors in field of automation and control. Discuss how their integration with other technologies can enhance their performance. This is a level 4 question. Revised Bloom's taxonomy level 4 question. Therefore, answer should be of that standard. Okay, so we need to analyze, not just giving definition, by hearted definition. We need to have our own analysis and analyze. One of my the answer is given. You can change the according to your perception view. Sensors play a critical role in automation and control by providing the necessary information for systems to operate in an efficient and effective manner. Okay, so in automation means wherever we make use of the machines in place of a man, we call it as automation. Using the machines to do the work. Then how we do? Suppose I measure the temperature by touching an element or touching it and checking whether its temperature is reached or not. I am using a thermometer to check temperature of a system. That is my work. I can do automation. I can use a small robot there which will check it the temperature. It will do. So my work, a person's work is replaced with a machine or a tool. We call it as automation. It's control of the automation. We need many sensors, because when I do, my hand, it touches and feels the temperature. Therefore my hand skin itself acts as the sensor. So when I want to convert it with a robot, automation comes, then there should be something which senses the same which a man is doing, or which is done by a person. Okay, so that is called as automation. So many industries is becoming automated nowadays. So there we need a lot of use of sensors. By continuous monitoring the environment and collecting data on various parameters such as the temperature, pressure, the flow rate, sensors enable systems to respond in a real time to change in their operating conditions. So we need the sensors to check what the real-time changes in the temperature or pressure or any flow rate. If any chemical industry, the flow of a chemical, continuous flow of chemical is the flow rate has to be controlled, otherwise reaction may not happen properly. A proper amount of chemical should be supplied, so the flow rate has to be measured. So this, to measure that, we need a sensor to have the real-time changes in the operating conditions. However, the performance of sensors can be enhanced by integrating them with other technologies such as artificial intelligence, machine learning, and Internet of Things. So, artificial intelligence, machine learning, and all these are new things, but you already know what it is. So, I no need to explain in detail. Artificial intelligence, that the intelligence that how the Homo sapiens, human beings, have got the intelligence power, trying to mimic by using the coding or by using the computer network to do something analyzing work, that is called as artificial intelligence. Machine learning, to make a machine, a robot, to work based on the data available, based on the analyzing power given by the making use of the data scientist and Internet of Things. For example, by leveraging machine learning algorithms, sensors can learn from their previous measurement and adapt to the changing conditions in order to improve their accuracy and reduce the false positives. So once we have the data, the already sensed data, if it is there, by using the artificial intelligence, whenever a new sensing method come, when the device has to sense something, then it will connect to the algorithm already which is there using the artificial intelligence or the machine learning algorithm. Then based on the previous measurement, it will cross check it and it will give the proper results than giving a false positive result in the real-time measurement. In addition, by connecting sensors to Internet of Things, it can be monitored and controlled remotely, allowing for greater flexibility and efficiency in operation. If we can connect the sensor to Internet of Things, that means we can operate it from a far distance. No need to a person no need to go near to that thing which we need to sense. It can be sent using with a robot. It can be sent and a person can control from a far distance, in a safer distance. It has got the flexibility and better efficiency in operation. For example, sensor integrated with the cloud-based platform can provide real-time data analytics and predict the maintenance, which can help reduce the downtime and improve overall system performances. Overall, the integration of sensors with other technologies can enhance their performance, enabling them to provide even more accurate, reliable, and efficient data for automation and control applications. The working principle of a conductometric sensors. Conductometric sensors are a type of a chemical sensor that measure changes in the electrical conductivity of a solution due to the presence of a specific analysis. So the word indicate conductometry, something related to electrical conduction. So if any changes in electrical conduction, that will be sensed by using the conductometric sensors. The working principle of conductometric sensor, it is based on the fact that the electric conductivity of a solution is related to the concentration of charged particles in the solution, such as ions or charged molecules. That means if the analyte which we want to analyze, if it has got a charged particle or such as ions are negatively charged or positively charged molecules, if it is present, it can show its movement in presence of a current charge. If a positive charge is given to an electrode, say so, then the negatively charged ions will go near to that positive charged electrode. Therefore, there is a movement of ions. Movement of ions creates the movement of electrons, so it is a conduction. So, or even charged molecular movement, it can be detected by using the conductometric sensor. So it is related to the concentration of charged particles, ion. Concentration means if more ions are there, more movement will be there. So more will be the conduction. And if the ions are smaller in size, then the smaller ions will move faster. Therefore, based on the size of the ion also the conductivity will vary. So this is the working principle behind the conductometric sensor mainly. It usually consists of the conductometric sensor usually consists of two electrodes made up of a conductive material such as metal, which is connected to a non-conducting material such as glass or plastic, which is covering only the metallic part will be in touch with the element which we want to sense. And when a voltage is applied across the electrode, the electric field is generated in the solution, and the charged particles in the solution begin to move towards the opposite charged electrode. Say example how to I'll try to take a pointer here, ball pointer. Okay, so suppose if you have a color, the color black will not work. I think red will work. Okay, if we have two electrodes, see these are the two electrodes which are conducting electrode, which is covered with a non-conducting cover like this. So my drawing is not proper because I am drawing with the mouse. Okay, so it is covered with a non-conductive element, and it is connected to a voltmeter like this connected, and it is dipped into a solution which contains the analyte. Okay, so this is the analyte. Okay, here these are the analyte. Okay, very good. Okay, these are the analyte, and the electrodes are dipped into the solution. Okay, this solution contains the ions or charged particles. So if you apply a voltage across these two electrodes which are in contact with the solution, the ion, suppose if I give a positive charge here, positive charge is applied on this left side electrode, that means the negatively charged ions will move towards that electrode. Clear? So that is clear. So movement of ions, the negatively charged ions will move towards that electrode, positive charged ions will move over to the opposite direction. Therefore there is a movement of ions, movement of the charged particle. Movement of charged particle create the that we call as the conduction is there. That conduction can be measured, how much movement of ions are present, that can be measured. Based on the conduction we can say which chemical is present there. Okay, so that is about the point 4. So when an analyte is introduced into the solution, it can interact with the charged particles in the solution, altering the overall conductivity of the solution. That means I already drawn in the previous one. When we introduce that analyte solution, to that electrodes dipped. Okay, when we introduce the analyte to the electrodes of the sensor, then the altering overall conductivity of the solution can be measured. Sixth point, this charge in conductivity can be measured as a change in the voltage or current across the electrode, providing a quantitative measurement of the concentration of the analyte. So you can even not only quality, you can even get exact quantity, how much ions present, how much is the solution concentration of that solution can be measured. Conductometric sensors can be used for a variety of applications, including the detection of ions, gases, and biomolecules. I think this experiment, it is there, hands-on experiment is there in your chemistry lab. We are having the conductometric measurement. We are using the conductometric sensor there. By using conductometric sensors, we are measuring the concentration of the solution in the chemistry lab. Okay, so conductometer, it can be used for a variety of applications, include detection of ions, gases, and biomolecules. They are widely used in medical diagnostics, environmental monitoring, industrial process control. Advantage of being simple to use, cost effective, and they are relatively sensitive in these conductometric sensors. However, they may be subjected to interference from other compounds in the sample and may require careful calibration to ensure accurate measurements. We have to keep on checking the instrument with a non-concentration of solution, whether the reading given is accurate or not. We call it as the process known as calibration, making the sensor ready for the actual sensing work. The conductometric sensor are calibrated each and every time. We need to calibrate the instrument before the practical application or use. Okay, this is a flow chart which shows the working of conductometric sensor. Apply voltage across two or more conductive electrode embedded in a non-conductive material, generate an electric field in the solution. Charged particles in the solution begin to move towards the opposite charge electrode. Then introduce the analyte into the solution. Analyte interact with the charged particle in the solution, alters the overall conductivity of the solution, which is measured. Measure the change in the conductivity as changing voltage or current across the electrode. So this just shows a flow chart. Okay, how this shows. This easy to understand. That's why I put it. Question: explain the working principle of conductometric sensor and the factor that affect their performance in detecting on a lighter. So it's a level 3 question. So answer is here. The same question is there. Conductometric sensors operate based on the changes in electrical conductivity when a chemical reaction occurs. Okay, so there should be some movement of ions. Movement of ions. It always follows with some chemical reaction will be happening in the solution. When the analyte of interest comes into contact with the sensing material or the surface of the conductometric sensor, a chemical reaction takes place altering the conductivity of the sensing material. Okay, that means if a chemical reaction takes place, okay, I'll explain the first point again because my previous explanation was different. If we have an analyte present with us, okay, so we want to check any chemical reaction of this analyte. So what we do, we make it to react with some other chemical. So this is I'm showing as a burette. Okay, so some other chemical is taken there that is added to this solution. So when another chemical added to the solution, if they are reacting, there will be a changing concentration of ion, or there will be a new ions are introduced after the reaction. That can be measured by using two electrodes, two conductive plate connected to a voltmeter. The changes in the ion concentration here, or based on the movement of ions, the voltage or current can be measured. That is the meaning of this first point. Okay, so when the analyte of interest comes into contact with the sensing material on the surface of the conductometric sensor, a chemical reaction takes place altering the conductivity of the sensing material. There is no chemical reaction with the electrode. A chemical reaction takes place within the material. The conductivity of the solution will be measured by using the because there will be a movement of electrons, so that is conduction takes place. The conduction is measured by using the electrodes. This change in conductivity is then measured and quantified, allowing the analyte to be detected. Fourth point, the performance of conductometric sensor can be affected by the nature of the analyte. For example, the sensitivity and selectivity of the sensor, it depends upon the chemical properties of the sensing material and analyte, as well as their affinity for each other. If the chemicals if they react properly, then there will be a change in conductance that can be measured. Okay, so it is if any other chemicals are present there, it will be interfering the reaction. So the performance of conductometric sensor, it can be affected with the nature of the analyte. The stability and reproducibility of the sensor signal can also be affected by factors such as temperature, humidity, as well as stability of the sensing medium. We know the conduction, it depends upon temperature. In general cases, we can say more the higher the temperature, higher the activity, higher the conductivity. Humidity also plays the same type of role. Humidity means more humid means more ions present in the atmosphere, uh, atmosphere or the solution. They are chemicals, elements are present. More humidity means more number of ions will be present. So it affects the conductivity measurement. It disturbs the conductivity measurement, or the one of the factor which affect the conductivity measurement or the conductivity sensor. Additionally, the design of the conductometric sensor, including the size and shape of the sensing element and the configuration of the electrode, can influence the performance of the sensors. Not only temperature sensor or the analyte, even the size of the material used, the sensing element used, the configuration of the electrode, how the electrodes are configured, it also will affect the performance. By improving the sensitivity, stability, selectivity, and reproducibility of the conductometric sensor, it can be used more effectively for a wide range of analytical and detection applications such as environmental monitoring, biomedical research, chemical processing, etc. Question based on that topic, that evaluate the strength and limitations of a conductometric sensor working principle in terms of its suitability for detecting different types of analytes and various applications. So it's a fourth level question, revised Bloom taxonomy level 4 question. Answer is given here. The conductometric sensor working principle has several strengths that make it well suited for detecting a wide range of analytes in various applications. For example, one major strength is its sensitivity, as even small changes in conductivity can be detected and quantified. The third point, additionally, the conductometric sensor working principle is relatively simple, requiring only a sensing material and a pair of electrode, which makes it easy to implement in different types of sensors. However, there are also limitations to the conductometric sensor working principle. Like one limitation is that the sensitivity and selectivity of the sensor can be affected by environmental factors such as temperature, humidity, which can lead to false positive results or false negative results. Another limitation is that the conductometric sensor working principle may not be suitable for detecting analytes that do not produce a change in conductivity, or that produces a change that is too small to be detected by the sensor. That means if the analyte is not having any conduction property, it is not having conductivity, it cannot be measured. Only the sensing, if the material or the solution, if it is having conductivity, change in conductivity, that's a little bit larger change in conductivity, then only it can be detected. On two small changes, it cannot be detected by using conductometric sensor. The suitability of the conductometric sensor working principle for different types of analytes and applications depends upon the specific requirements of the detection task. For different tasks, we should have a different sensing material. Eighth point say that, for example, applications where high sensitivity and selectivity are critical, such as in medical diagnostics or environmental monitoring, conductometric sensor may be well suited. However, in applications where other factors such as cost, speed, or ease of use, the easiness of the usage, if they are more important, then we have to go for other sensor than conductometric sensor. By understanding the strength and limitations of the conductometric sensor working principle, researchers and engineers can make informed decisions about the design, use of conductometric sensors in various applications. Next topic, that is engineering applications of conductometric sensors. This is the last topic of this particular class video. Conductometric sensors have a wide range of engineering applications. Some of the examples are given here. First example, environmental monitoring. Conductometric sensors are used to detect and measure the concentration of pollutants in air, water, and soil. For example, they can be used to measure the concentration of nitrogen oxide or carbon dioxide, or nitrogen oxide in the exhaust gas from vehicles, or to detect the presence of heavy metals in water. Water analysis, it can be used. For food processing, conductometric sensors are used in the food industry to measure the concentration of salt or sugar and other compounds in food product. They can also be used to detect the presence of harmful bacteria in food. This is mainly in the food industry very much useful. Otherwise, earlier days, it was depending upon the ability of a person, his ability to taste the amount of salt, presence of salt or sugar. Now we can have a sensor which we can preset the required how much salt required. If you preset, it will keep on checking it. Every slot of the product comes from the food industry, it will be automatically checking. Or if at all any changes needed, immediately it will indicate. So it's a type of automation system which sensors are needed. Medical diagnostics. Conductometric sensors are used in medical diagnostics to measure the concentration of ions or biomolecules in the body fluids such as blood, urine, or saliva. So this also done by using conductometric sensor. Example, the glucose level in blood or diabetic patient, it can be measured by using conductometric sensor. These are all treated as the application, mainly engineering applications, because engineers do different innovative products in which they need the different type of sensors. One of that sensor is a conductometric sensor. Industrial process control. Conductometric sensors are used in many industrial processes to monitor the concentration of chemicals in solution. It can be used to optimize the production of chemicals, pharmaceuticals, and other products. No complications, straight away the point is given. Gas sensing. Conductometric sensors are used in gas sensing applications such as detecting the presence of toxic gases in an industrial setting or monitoring air quality in indoor environments. Question based on that. Describe the various engineering applications of conductometric sensors in industries and how they contribute to the improving process efficiency. It's a level 3 question. Answer is given. First point of the answer. Conductometric sensors are widely used in various engineering applications, includes chemical processing, environmental monitoring, and biomedical research. In chemical processing, conductometric sensors are commonly used to monitoring the concentration of reactants and products, as well as for detecting impurities present in a reaction or in a process stream. This helps to improve the process efficiency by ensuring that reactions occurs at the desired rate and the product quality is consistent and meets the specification. Uh, if any chemical reaction in a chemical processing industry, chemical reaction presents, if at all any impurities are present or impurities are produced as a byproduct, the tunnel has to be detected immediately, otherwise the whole reaction setup will be disturbed. Finally, the product which is coming out, its quality um, will not be the same as we expect. Point number 3, in environmental monitoring, conductometric sensors are used for detecting the presence of pollutants in air, water, and soil. By providing real-time data on pollutant level, conductometric sensors enable more effective monitoring and management of environmental hazards, reducing the risk of exposure to harmful substances. Fourth point, in biomedical research, conductometric sensors are used for various applications such as monitoring cellular metabolism, detecting biomolecules, and measuring changes in pH or ionic concentration. By providing the precise or real-time data on physiological and biochemical process, conductometric sensors contribute to the improving our understanding of disease mechanism and the development of new therapeutic strategies. Straight away point is there, no need of further explanation. Overall, the use of conductometric sensors in various engineering applications help to improve process efficiency, reduce cost, and enhance safety and environmental sustainability. By providing accurate and reliable data, conductometric sensors enable more effective monitoring and control of industrial process, environmental hazards, and physiological and biochemical processes. Subscribe to my YouTube channel, My Intuition. The logo of My Intuition is given, My Intuition 4865, and support me to produce more and more results.